Welcome to this lecture on NPUs and how they turbocharge AI workloads. Today we'll walk through why specialized neural processors matter, how they're architected, and where they make the biggest difference in real products. Think of this as a high-level tour from basic design choices to practical deployment, with examples that show measurable gains and on-device possibilities. This slide contrasts general-purpose CPUs and GPUs with specialized NPUs, using a chip diagram to highlight wasted logic, wide floating-point units, and off-chip memory in general-purpose designs versus compact, low-precision MAC arrays and on-chip SRAM in NPUs. The takeaway is simple. NPUs trade unused general-purpose features for streamlined data paths and memory, yielding far lower power use and many freed compute cycles. Here, we break down the NPU into its key functional blocks, as shown in the diagram. Tiled MAC arrays deliver massive parallel multiply, accumulate throughput, distributed L1 caches, keep weights and activations local, DMA engines move data without wasting core cycles, programmable vector or shave units handle custom ops, and an MMU isolates context for secure, multi-tenant inference and safety. NPU efficiency comes from three practical mechanisms demonstrated on this slide. Fine-grained 8-bit MAC parallelism schedules thousands of ops per cycle. Sparsity engines and zero-value bypass skip wasteful computation, and dynamic voltage, frequency scaling matches power to demand. Together, these techniques enable sustained teraops performance while keeping power in the milliwatt range, ideal for battery-powered edge devices. This pipeline diagram shows how NPUs collapse layer latency for CNNs, transformers, and RNNs by streaming weights into MAC arrays, fusing batch norm and activations, and writing output tiles to SRAM. The result is much lower per-layer delay and real-time outcomes like sub-10 millisecond image classification and on-device speech-to-text that work without a cloud connection, improving responsiveness and privacy. We're seeing an evolution from inference-optimized NPUs toward hardware that can support on-device fine-tuning. Current chips focus on quantized weights and efficient inference, while next-generation designs add tiled architectures, local gradient computation, and mixed precision MACs. That shift promises privacy-preserving personalization, letting devices adapt models locally with tiny power budgets and without sending user data to the cloud. On-device NPUs unlock a host of consumer applications across smartphones, laptops, and IoT gadgets. Think real-time language translation and generative photo edits on phones, AI-enhanced creative tools and noise cancellation on laptops, and edge analysis, and smart home automation for IoT. The shared benefits are low latency, preserved data sovereignty, offline capability, and extended battery life through CPU offload. This hybrid workflow diagram explains how TPUs and NPUs complement each other. Large models and massive batch training happen in cloud TPUs, then models are compressed and optimized for the edge, and NPUs handle low batch, low-latency inference on devices. The end-to-end pipeline balances cloud scale with edge responsiveness to deliver efficient, real-time AI applications. Real-world NPUs already show measurable gains. Apple's Neural Engine delivers about 15 times faster Face ID and live captioning performance. Qualcomm's Hexagon reports 45 tops for Snapdragon X Elite, enabling Windows Studio effects, and Intel's Core Ultra NPU can free roughly 40% of CPU cycles for background tasks. These are practical improvements that users notice in responsiveness and battery life. Embedded NPUs are transforming real-world use cases, like manufacturing, quality control, with millisecond defect detection, portable on-device ultrasound segmentation for medical imaging, and retail shopper flow analytics that reduce power and cost. Compared with GPU-based gateways, embedded NPUs shift compute to the edge, cutting latency, improving privacy through local processing, and lowering total system cost across these applications. Looking forward, Three technical trends drive ubiquitous generative AI. Advanced 3-nanometer process nodes, giving huge performance per watt, chiplet architectures with UCL-style interconnects for heterogeneous tiles, and sparse exploiting transformers that enable large model inference locally. Together, these frontiers make high-density, low-power AI feasible in small devices and open the door to real-time, on-device generative experiences. For practical NPU deployment, think strategically. Select NPUs for latency, sensitive, power, constrained, or privacy. Critical workloads, treat them as co-processors that offload matrix-heavy tasks rather than full CPU replacements. Optimize models through quantization and pruning. Leverage vendor compilers and efficient tiling to maximize SRAM reuse. And plan a hybrid cloud-to-edge pipeline to balance scalability with real-time performance.